Welcome back to The Explainer, where we evaluate the literal building blocks of our civilization. And you know the rules by now. We don't give out nostalgia points here. We strictly judge materials based on their real-world utility and their actual impact. Today, we're putting the unsung hero of composites on trial, fiberglass. We are fresh off ranking graphene, the atomic wonder material of the future. But today, we're grounding ourselves with a gritty, everyday workhorse composite, a material that quietly powers modern transportation and, frankly, our entire renewable energy grid.
Think about it for a second. What material single-handedly gives us the ability to construct massive renewable energy structures, like wind turbine blades longer than an entire football field, and lightweight vehicles, all at a fraction of the cost of its rivals? We're talking about a material that totally revolutionized modern boating because it simply refuses to rust in salt water. It's incredibly strong, it's highly affordable, and if you look closely, it is absolutely everywhere.
So here is our roadmap for today. We'll start with number 1, what is fiberglass? Move to 2, the historical breakthrough. 3, engineering the specs. 4, powering the modern world. 5, flaws in delamination. And we'll wrap up with number 6, the final verdict. Kicking things off with section 1, what is fiberglass? Let's quickly define this fiber matrix system. Okay, so the absolutely crucial point here is that this is a synergistic system. Think of it like a really successful partnership. On one side, you have these incredibly fine strands of actual glass. Those fibers do the heavy lifting. They provide the raw, physical, structural muscle and stiffness. But obviously, you can't build a boat out of loose, floppy glass fibers, right? That is where the polymer resin matrix comes in. Usually made of polyester, vinyl ester, or epoxy, this resin surrounds those glass fibers, holds them perfectly together in whatever shape you mold them into, and protects the glass from outside damage. It is just a brilliant marriage of structural strength and protective glue. Moving right along to section 2, the historical breakthrough. We're going from insulation to the oceans. It's kind of wild to trace how fiberglass quietly evolved over the decades. Back in 1932, researchers at Owens Corning developed the very first continuous glass fiber. Then, rolling into the 1940s, wartime necessity pushed things into overdrive. The military started using it for aircraft components and radar domes, radomes, because it was insanely lightweight, and crucially, it didn't block electronic signals. Fast forward to the 1950s, and it sparked an absolute explosion in consumer pleasure boat building. And then jumping ahead to the 2000s, it saw this massive exponential growth by becoming the undeniable backbone of the modern wind energy revolution. And I just find it so fascinating to note that as early as 1942, the very first all-fiberglass boat hull was successfully produced. This was a massive turning point. It literally saved boaters from the endless, back-breaking nightmare of sanding rusted metal and replacing rotted-out wood. It totally democratized boating, making hulls affordable, lightweight, and incredibly durable against the harsh marine environment. All right, section 3, engineering the specs. Let's review this composite's mechanical resume. Fiberglass boasts this virtually unbeatable balance of extreme structural strength and flexible manufacturing. Get this, by weight, fiberglass is actually stronger than steel when you pull it in tension. No way, right? Combine that intense strength with outstanding corrosion resistance against salt and harsh chemicals, a very low thermal expansion rate, and the fact that it is highly workable. You can spray it, you can hand lay it, or mold it into incredibly huge, complex, swooping shapes. It is an engineer's absolute dream material. Which brings us to section 4, powering the modern world. This is where it becomes the unsung hero at scale. As of March 2026, global production exceeds a staggering 6 million tons per year. Just let that sink in for a moment. 6 million tons of a highly specialized composite material. That proves just how foundational, ubiquitous, and heavily relied upon this material truly is all across the globe. From colossal turbine blades sweeping through the air to the hulls of practically every modern recreational boat on the water, to the body pails of affordable sports cars and commercial truck cabs, fiberglass is powering the green transition and modern transportation at a massive, undeniable scale. Plus, it's hidden all around us in construction. It forms giant chemical storage tanks and corrosion-resistant piping. It is quite literally holding together the background infrastructure of the modern world. But it's not all sunshine and perfect specs. Section 5, flaws and delamination. It is time for the brutal truth. The unavoidable truth here is that while it's a highly reliable workhorse during its actual lifespan, its thermoset resins make full recycling incredibly challenging. Unlike aluminum or glass that you can just melt down endlessly, once that resin cures, it is permanently set, and that leads to a very messy retirement. We're talking old boat hulls and wind blades piling up in landfills. It can also suffer from UV degradation, ugly blistering if moisture gets under the gel coat, and, under repeated cyclic stress, the layers can suddenly just separate, which is a catastrophic failure known as delamination. Oh, and if you've ever had to cut or grind it, it produces this highly irritating, hazardous glass dust. If you've ever been in a hot attic with pink insulation, just multiply that itch by 10. And of course, we have to talk about its flashy cousin. When pitted directly against carbon fiber, fiberglass definitely loses in absolute strength and weight savings. Carbon fiber is lighter and offers extreme stiffness, which is why it's used for aerospace and Formula One cars. But here is the kicker. Fiberglass completely dominates on affordability and broad scalability. You aren't going to build a fleet of 10,000-gallon chemical tanks out of carbon fiber. The economics just simply don't work. Fiberglass is the composite of the masses. All right, the moment of truth. Section 6, the final verdict. Let's calculate its tier placement. Looking at our 6 stringent criteria, you can clearly see that its incredible workability, scoring a massive 9.5, and its cost-effective scalability at a 9.0 really do the heavy lifting for its overall grade. Its historical impact and mechanical properties are strong at a solid 8.0, and its sheer versatility across completely different industries is undeniably top tier. So, averaging those categorical scores out gives us an 8.7 out of 10. Honestly, this is a highly respectable grade for a composite material that wrestles with such known sustainability and recycling challenges. And it's definitely worth noting that the industry in 2026 is aggressively pushing recycled fiberglass content and bioresins to offset these very flaws, which keeps its lasting relevance score impressively high. And that officially lands fiberglass in the high A tier. Look, it isn't the sexiest or the absolute strongest material out there, but if Kevlar saves lives and carbon fiber wins races, fiberglass is the undisputed champion that powers the green energy transition at a scale that actually matters to the planet. It earns its spot through sheer affordable utility. If you take away anything today, I want you to remember this. Without fiberglass, we would be stuck with significantly smaller, vastly more expensive wind turbines, radically heavier boats, and a much, much slower renewable energy rollout globally. It strengthens our future, and it does it affordably and reliably. So what's next? We'll find out in our next explainer as we evaluate an ancient, simple mineral that preserves our food, melts ice on our winter roads, and builds foundational chemical empires across the globe. But for now, I want to know what you think. Do you agree with fiberglass sitting in the high A tier? Is it the ultimate workhorse composite, or should those brutal recycling flaws drag it down to the B tier? Drop your thoughts below, and I'll see you in the next explainer. Keep learning.